Hi everyone, welcome to chapter 9. We are going to talk about oxidation reduction reactions today, which we have talked about already in the course, but today we are going to look specifically at how to balance these redox reactions. They are not as straightforward as balancing normal reactions because we have to also go through and balance the charges. A lot of times in redox reaction we have charged species. So today we're going to talk about the rules for balancing redox reactions and go through a bunch of examples. So a little bit of review just to remind us all what redox reactions are. So redox reactions are electrochemical reactions, and the electrons are being transferred from one species to another. So they're going, oftentimes from one metal to a different metal is kind of what happens. And this is done in solution. So we have something that's being oxidized. And so when we have something being oxidized, it loses electrons. And again, this is called the reducing agent because it's causing something else to be reduced. And then we also have something that's being reduced, and the thing that's being reduced is gaining electrons, and we call this the oxidizing agent because it's causing something else to be oxidized. These oxidation and reduction processes are always occurring together, never in isolation. They're like equal and opposite. So if something is being oxidized, then something else is being reduced. You can't just have something being oxidized, or you can't have like two things being oxidized because, if something is gaining electrons, right? If something is being reduced, it had to gain them from somewhere, so then something else had to lose them, right? Something else was oxidized. So these always occur in pairs. In order to figure out what's being oxidized and what's being reduced, we have these oxidation numbers. And again, we've talked about these before. So any singular elements like zinc here, zinc is sitting by itself and it doesn't have a charge. So that means zinc has an oxidation number of 0. Hydrogen is sitting by itself, but it has a positive charge, so it is a +1. Zinc over here is sitting by itself. It has a 2+ charge, so its oxidation number is +2. Just as a reminder, whenever we write charges, we write the number first and then the sign. Whenever we write oxidation states, we write the sign first and then the number. It's not super important right now, but if you go into higher levels of chemistry, they may be picky about it. And then over here, this hydrogen is a diatomic element, and it's neutral, right? It doesn't have a charge, so its oxidation state is 0. So looking at this, zinc is going from a 0 to a 2+, which means it lost 2 electrons. So since zinc lost 2 electrons, that means it is being oxidized. So remember, you can think of oil rig, right? Oxidation is loss, reduction is gain. Or you can think of Leo says Ger, right? So loss equals oxidation, gain equals reduction. Either way, you need to remember, or you need to have a way to remember that if something is losing electrons, right, it's becoming positive. That means it's being oxidized. And here, hydrogen went from a +1 to a 0, which means it gained an electron. So it gained an electron, which means that it is being reduced. Okay, so you need to make sure you've got all of those definitions and things straight. So here's our rules for assigning oxidation numbers if you've forgotten them. Free elements, uncombined state, right? So this is ones that are just kind of chilling by themselves, have an oxidation number of 0. So this was like in the last slide when we saw like zinc or hydrogen, right? They are not combined with any other elements. They have an oxidation state of 0, and they are not charged. This includes things like hydrogen is a diatomic, right? We remember those, Hofbrinkel. So any elements in there can exist as diatomics, but they're not bonded to any other elements, right? They're bonded to the same element. So we still call them free elements. They still have oxidation numbers of 0. So here's more. If we have a monatomic ion, so a single element that is charged, then the oxidation number is equal to the charge. So like, if we have Li+, then that means it's, Li+ is a +1. And Fe3 plus, that means Fe3 plus is a +3, O2 minus, which means O2 minus is a -2. Okay, so if you have an ion sitting by itself, then the charge is equal to its oxidation state. The oxidation number of oxygen is usually -2, like 99% of the time. The only exception is in hydrogen peroxide, right? And so we have peroxide, or well, I guess any other peroxide. Anytime you see a peroxide, you have O2 2-, then the oxidation number is -1. All other instances, oxygen is always a -2, just this one exception where it's a -1. The oxidation number of hydrogen is always +1, except when it's bonded to metals in compounds. So like this is called lithium aluminum hydride, right? Lithium aluminum, and then the H, since the end is hydride. So if hydrogen is bonded to a metals, then it can be a -1. This is going to be really unusual in this class. You can pretty much just go with the fact that hydrogen is always going to be a +1. This is just if you see it in later classes. If hydrogen is bonded to a metal, it can be a -1, which again, I think is strange considering what we've learned for this class so far. If you have a group 1A metal, so these are alkali metals. Alkali metals are always +1. Alkaline earth metals, so any group 2A, are always going to be +2. And fluorine is always a -1. So these will help you out, right? And then those are like our hard and fast rules, right? When we covered this in lecture, we talked about a bunch of other rules, right? Like chlorine is usually this, or nitrogen is usually that. These ones are just kind of our hard and fast rule. You can go back and review the other ones if you'd like. But if you remember these rules and the fact that the sum of the oxidation numbers of all the atoms in a molecular ion is equal to its charge, you can solve for all of the rest of them. And if it's neutral, then it's going to be 0. But, so if you remember these rules, and then, you can solve for any other elements that you may come across. This is probably the easier way to do this. So go ahead and pause here and identify the oxidation numbers of the elements in bicarbonate. All right. So hydrogen, since hydrogen is not bonded to a metal, hydrogen is going to be +1. Oxygen, since it is not a peroxide, oxygen is going to be -2. And so we can use these to figure out what carbon might be, because carbon was not one of the rules that we covered. Carbon can change oxidation states fairly easily. So the way that we do this is we make kind of a chemical equation, right? So hydrogen is +1. Or here, let's back this up even farther. If we go hydrogen plus carbon plus 3 times our oxygens, that's not a 0, that's oxygen, is going to equal -1. That's the charge on the compound. So hydrogen is +1 plus carbon, we don't know, plus 3 times oxygen, which is -2, is going to equal -1. So we've got +1 and essentially -6, so that's going to be -5. So carbon -5 equals -1. So if we add 5 to both sides, we get that carbon is +4. So that's how you would go about solving for elements if you don't know what their oxidation numbers are. So now, really getting into what we're going to talk about today is balancing these redox reactions, balancing oxidation reduction reactions. There are a couple different ways to do this. I'm going to show you the easiest way, and this is called the half reaction method. So if you need more help with this and you want to Google it, it's called the half reaction method. And the way that we do this is we essentially break the reaction into 2 different parts. We're going to look at oxidation and we're going to look at reduction, and we're going to balance them separately and then combine them together at the end. If you go on Canvas, right, we're going to go through these rules for balancing redox reactions. But if you go online on Canvas and find the rules for balancing redox reactions just page, I have all of the rules written out there for you, so you can follow those when you're working through it. Please note, though, you will not have access to this when we're doing quizzes and tests and things like that. So you do need to commit these to memory. You do need to know them. That being said, you're going to have a fairly lengthy worksheet to work on to really drill this into your head. Okay, so balancing redox reactions. So here's a particular problem. Balance the oxidation of iron 2+ to iron 3+ by dichromate in an acidic solution. And I would tell you what this goes to. So here's the reaction. I would give you this, this unbalanced reaction, because I didn't tell you that this was going to make chromium 3+. Okay, and that's not fair. You can't predict that at this point. So you would be given this unbalanced reaction, and I would ask you to balance it. So the way that we're going to do this is we are going to split this into two different reactions. We're going to write one reaction that deals with the iron and one reaction that deals with the chromium. So if we look at the oxidation, right, that would be iron. Iron is going from a 2+ to a 3+. It is losing one of its electrons. It's being oxidized. So therefore, by default, chromium becomes our reduction, right? So in this oxidation one, we are writing anything that has to deal with iron, and the second one, we're dealing anything that has to deal with chromium. Don't worry about the oxygen for now. We are actually going to go through and balance oxygens later. So pretty much when you're breaking these apart, you're going to look at the metals. What are the metals doing? So after you break them into your half reactions, you're going to balance the atoms other than oxygen and hydrogen in each half reaction. We have ways of dealing with oxygen and hydrogen later, so we're just going to balance the ones that are not that. So if we look at the iron reaction, there's one iron on each side, so we don't have to do that step. But for the chromium one, on the left side we have 2 chromiums. On the right side we only have 1. So we'll balance our chromiums by adding a 2 out in front of chromium 3+. Our next step would be to add water to balance out the oxygen and hydrogen. Add water to balance out the oxygen atoms, and then add H+ to balance out the hydrogen atoms. Okay, so we need, so in looking at the ones before, so I'm just going to write these at the top. We had our iron reaction was Fe2+ to Fe3+, and so far we balanced our chromium, so we wrote Cr2O7 2- gives us 2 Cr3+. So again, we're going to go ahead and ignore the iron reaction for now because there's no oxygens that need to be balanced and there's no hydrogens that need to be balanced. But if we look at our chromium reaction, right, our chromium reaction has 7 oxygens on the left and no oxygens whatsoever on the right. So right now we're not obeying the law of conservation of matter. So the way that we fix this is, since we have 7 oxygens on the left, we are going to add 7 waters on the right to balance out those oxygens. So now we have 7 oxygens on the left, 7 oxygens on the right. But now you'll notice that we have hydrogens on the right, but no hydrogens on the left. So we are going to add H+ to balance the hydrogen atoms. So we have, on this side, we had 14 hydrogens. So to balance it, we are going to add 14 H+ to the other side. So now, looking at this, we have 2 chromiums on each side, 7 oxygens on each side, and 14 hydrogens on each side. So we're good to go. Now, we are going to add electrons to one side of each half reaction to balance the charges on the half reactions. This is the step that people do wrong because they add up the charges wrong, which sounds silly, but it happens. So if we look at the iron reaction first, right, this one, we've kind of been ignoring it for now because we didn't need to balance anything, but our charges aren't balanced. So if we look on the left, we have Fe2+, and the other side we have Fe3+. So our charges aren't balanced. On the left side, we have a 2+ charge, and on the right side, we have a 3+ charge. So you're always going to go to add electrons to the side that is more positive or less negative. that's how you're going to know where to add electrons. You're going to add it to the one that is more positive or less negative, because essentially, right, you can only add electrons. So we see we have 2 plus and we have 3 plus. We're going to add it to the more positive side, so we're going to add 1 electron to the right side. So when we add up the charges on the right side now, 3 plus plus 1 minus gives us 2 plus on the right, which equals the 2 plus on the left. So now our charges are balanced as well. And then we're going to do the same thing now with our chromium reaction. So if we look at our chromium reaction, on the left-hand side, we have 14 H+, which means we're getting 14 positives, plus the charge on that dichromate is 2 minus. So total on this charge, we get 12 plus, okay? Or plus 12, however you want to write that. So, but we're getting 12 positives on this left side. 14 positives plus 2 minus gives an overall 12 positives. And on the right-hand side, we have 2 times the 3 plus, which gives us 6 plus. Oops. And then we plus, the water is neutral. So overall, we have 6 plus on this side. So again, we're always going to add electrons to the more positive or less negative side. So we're going to add electrons to the left until it equals the right. So we're going to add 6 electrons to this 12 plus, so that we get a 6 plus charge on each side of the reaction. The next step will be to make the electrons equal, right? Because we need them to balance out. So here we have 6 electrons and we have 1 electron. And so we need to make the electrons equal, because right now they're not. In this the next step is going to, or the one after we balance the electrons, we're going to end up canceling them out. So you need to have the electrons be the same number so that they'll cancel out. It's kind of, looking ahead. Just as like a note, when you're writing these reactions and you're adding electrons, one of the reactions will have the electrons being added to the left-hand side. The other reaction will have it being added to the right-hand side. The electrons will always be opposite. If you have electrons in both reactions being added to the left, or both reactions added to the right, you've done something wrong. Go back and fix it. So here we have electrons on the right, electrons on the left, so we are good to go. In this next step, like I said, we're going to need our electrons to be equal. So what's going to happen is we are going to multiply this whole reaction by 6. So that we are going to end up with 6 electrons here and 6 electrons here. We need our electrons to be equal. So when we do that, right, we're going to multiply that first reaction by 6, but we're not going to do anything to this second reaction because, we're trying to get them equal. So now, though, we have 6 electrons here and 6 electrons here, which is what we need so that they will cancel out in the next step. So now it says to add the 2 half reactions together and balance the final equation by inspection, okay? So when I add them together, I'm essentially adding them straight down, kind of like what we did in Hess's law. Okay, we're going to add them together. So since the electrons are on opposite sides of the reaction, right, they're going to go ahead, here, I've got this here. The electrons are on opposite sides of the reaction, so they're going to cancel out. They're going to be gone. Okay, and now we can just add them straight down. So everything on the left still needs to end up on the left side of the arrow. Everything on the right still needs to end up on the right side of the arrow. So our reaction looks like this, which is a lot. But that's how you balance redox reactions. Right now, you're probably thinking, wow, that's a lot of steps. It's a lot of work. I don't know how I'm ever going to remember this. And the answer is repetition. You are going to do lots and lots and lots of these problems, and it will come more naturally and it will go faster. So just hang in there. We've got a couple more example problems going on. So if you have seen balancing redox reactions before, I would go ahead and pause here and try these out on your own. If this is the first time you've ever seen balancing redox reactions, I would watch through the first one of these examples and then maybe try the second one on your own. But, this is kind of a choose your own adventure, so do what you need to do. But it says to balance each of the following redox reactions in acidic solution. So far, that's what we've been doing. We've been learning how to balance them in acidic solution. We'll talk about how a basic solution will change things after these two example problems. So, like I said, if you're feeling confident, go ahead and try it. Otherwise, go ahead and stick around. So, the first thing we need to do is break it into two half reactions. We're going to write one reaction to deal with the cobalt and the other reaction to deal with the nickel. So our cobalt reaction looks like this. And our nickel reaction looks like this. I'm leaving out the states of matter for now, just to make my life easier when I'm writing through these. You're welcome to include them if you want, or just include them down at the bottom when you write your final answer. So then our first step would be to balance all of the elements except for oxygen and hydrogen. If you'll look, in our cobalt reaction, we have one cobalt on each side, so we're fine. In our nickel reaction, we have one nickel on each side, so we're fine there as well. We don't need to go through the steps of balancing the oxygens. We don't need to go through the steps of balancing the hydrogens because they don't show up, so we can just kind of skip all of those steps. The next step that we actually need to pay attention to, and again, if you go on Canvas, all of the rules for balancing these redox reactions are in a document there, and it may be helpful to have that out so you can reference it as we're going. But now we're going to go through and balance the charges. So in the cobalt reaction, we have a 3+ on the left and a 2+ on the right. And again, we're always going to add electrons to the more positive or less negative side because, we can only add negatives. So we'll add one electron to this side so that they are both now a 2+, right? So we have a 1- plus a 3+ gets us a 2+ on the left, which will equal a 2+ on the right. And then nickel, our nickel reaction, right? We have the left side is 0, right? It's totally neutral. And the right side has a 2+. So we'll add 2 electrons to this right side, so it will be neutral as well. 2+ plus 2- gets us 0. Our next step is to go through and make sure our electrons cancel out. So we have 2 electrons in the bottom reaction and only 1 electron in the top. So we're going to go through and multiply this whole reaction by 2. And so when we do that, that means we're going to get, we'll get 2 electrons plus 2 cobalt 3+ gives us 3 cobalt 2+. So I'm going to just kind of do that. So now we have 2 electrons here and 2 electrons here, which means that they will cancel out and we are ready to combine our reactions. So we're going to add them together. So 2 electrons cancels 2 electrons. And then we'll go ahead and write everything on the left and then everything on the right. So we have nickel plus 2 CO3+ gives us Ni2+ plus 3 CO2+. And it doesn't matter what order you write them as long as they end up on the left-hand or the right-hand side of the arrow. And then, like I said, I would go in and fill in the states of matter since we do know them. So that would be how you balance this reaction. Pretty easy since we didn't have any oxygens or hydrogens floating around. It was pretty straightforward. The next reaction, though, is not so straightforward. As you can see, we've got oxygens and hydrogens, so this one looks like it will be more fun. So we're going to write 2 different reactions. One of them will deal with the manganese, and the other one will deal with the copper. So our manganese reaction will be MnO4- to Mn2+. And our carbon reaction, right, will be this guy to carbon dioxide. So our first step is to balance all of the elements except oxygen or hydrogen. So if we look at the first reaction, our manganese are balanced, and we look at the second reaction, our carbons are balanced. So we're good to go on that step. Our next step will be to balance the oxygens by adding water. So in the first reaction, we have 4 oxygens on the left, so we are going to add 4 waters on the right to balance out those oxygens. And then thinking about this second equation, right, the carbon equation, we have 2 oxygens on the left, 2 oxygens on the right, so we don't need to add waters anywhere. Our next step will be to balance the hydrogens by adding H+. In the first reaction, we have 8 hydrogens on the right, so we are going to add 8 H+ to the left to balance the hydrogens. So now our manganese are balanced, our oxygens are balanced, and our hydrogens are balanced. In our carbon reaction, the second reaction, we have 2 hydrogens on the left, so we're going to add 2 H+ on the right. So then our carbons are balanced, oxygens are balanced, hydrogens are balanced. Our next thing is to go through and balance the charges. So if we are looking at the first reaction, on the left-hand side, we have an overall charge of 7+ because we have 8 positives and 1 negative, so overall, this whole side has 7+. If we are thinking about the right-hand side, overall our charge, right, we have a 2+ plus 0, so overall we have 2+ on this side. So we're always going to add electrons to the more positive or less negative side. So we're going to add them to the left, and we're going to add 5 electrons. So now this is a 2+ charge, just like the other side, right? 2+. So now both sides have an overall charge of 2+. In looking at the second reaction, the left-hand side is neutral, and the right-hand side has an overall 2+ charge from those 2 hydrogens. So we're going to add 2 electrons to the right-hand side to make it neutral as well. So now we have, we've balanced our charges, we've balanced our elements, so now we need to go through and balance the electrons in the 2 reactions so that we can combine them. We have 5 electrons in the first reaction and 2 electrons in the second reaction, so that means both will need to go to 10 electrons in order for us to combine them. So we're going to multiply this whole reaction by 2 and this whole reaction by 5 to get those electrons to be equal. So I'm going to rewrite this down below. So we'll have 10 electrons plus 16 hydrogens plus 2 MnO4 minus gives us 2 Mn2 plus 8 waters. And our second reaction will be 5 and 5. All right, so now we have 10 electrons on in both reactions. And you'll notice, again, like I was saying earlier, the top reaction has electrons on the left and the bottom reaction has electrons on the right. You always need to have them on opposite sides. If they end up on the same side, you've done something terribly wrong, so go back and fix it. So now we're going to add them together. So our 10 electrons cancels our 10 electrons, which is all good to go. But if you'll notice, we also have hydrogens on both sides of the reaction. So we have 16 H+ here. We have 10 H+ here. So kind of thinking about what we talked about when we were doing Hess's law, right? They can cancel out. So overall, right, if we subtract 10 H+ from both sides, these will be gone. And we'll be left with 6 H+ left over. Okay, so you always need to pay attention to those, the H+ and the waters. Okay, those are the 2 things that'll really show up with this. So our overall reaction will be 6 H+. These will be aqueous floating around, plus 2 MnO4 minus, plus 5. Plus, I'm going to continue this. Oh, I lost my arrow. Sorry, this should be an arrow. Sorry, guys. And I'll continue this underneath it. And then always remember that water is a pure liquid, so it will get an L. So there you go. That is how you go through balancing reactions in acidic solution. Those are your series of steps. Again, like I said, you're going to get lots of practice following these series of steps because you have lots of practice problems. So sometimes, though, we will have them in basic solutions. And before you panic and think you have to learn a whole new set of rules, basic solutions, we're just going to add on a couple steps. So you're going to do everything that you do for the acidic solutions, and then you're going to add on a couple more steps for basic solutions. So the beginning is always the same. So for the basic solutions, take your final reaction. So like the one that you wrote, this one, right, at the bottom, this final reaction. You're going to take this final reaction that you wrote, and you're going to add hydroxide to both. Look at, this is important, both sides of the equation for every H plus that appears in the final equation. So like in this last reaction, we ended up with 6H plus over here on the left. So we would add 6 OH minus to each side, okay? Just don't forget to add them to both sides. People regularly forget to do that, and they'll only add it to the side with the H plus. So be very, very careful. You're going to add OH minus to both sides of the equation. So here's an example that we had earlier, right? So if we ended with 14H plus on the left. So you would add 14 OH minus to both sides of the equation. And what happens is that this 14 OH minus and the 14 H plus, they combine together and they make 14 waters. Okay, they neutralize each other. So then you have to go through and reduce the number of waters, because if you'll see, we have 14 waters on this side and we have 7 waters on this side. So we can go through and subtract 7 waters from each side. And when we do, right, we're going to, subtract these 7 H2Os, subtract these 7 H2Os, and that will get us this, right? So these waters will be gone. We'll be left with 7 water on the left, and we'll keep our 14 hydroxides that are new on the right. That's it. That's all that's new about the basic reactions, okay? So you're going to do everything the same that you do in acidic reactions. Just at the end, you're going to add some hydroxides, cancel out your waters. That's it. So that's the only thing that's different. Let's try it out. So if you're feeling confident, like I said before, go ahead and pause here. You can try these out on your own. If you're like, I could use an example or two, then stick around and I'm going to go through them. So in the first reaction, right, in this first example, we need to separate our metals. So we're going to write one reaction that deals with the aluminum, and we'll write one reaction that deals with the chlorine. Our first step is to balance all of the elements except oxygen and hydrogen. So our aluminums are balanced. We have 1 on each side, but our chlorines aren't balanced. We have 2 chlorines on the left and only 1 on the right. So we'll add a 2 there. Our next step would be to balance any oxygens by adding water, which we don't need to do. There's no oxygens anywhere. And then we'll balance the hydrogens by adding H+. Again, we don't need to do that. There's no H+, or there's no hydrogen anywhere. Then we're going to balance the charges by adding electrons. So in the first reaction, we have a neutral charge on the left and a 3+ charge on the right. We're always going to add electrons to the more positive or less negative side. So we're going to add them to the right. And so we're going to add 3 electrons so that this side is also neutral. So now we are neutral on the left, neutral on the right. For the second reaction, we have a neutral species on the left and an overall 2- charge on the right. So again, we're going to add electrons to the more positive or less negative side, right? So neutral is our less negative side. So we're going to add 2 electrons to the left here. So now we have an overall 2- charge on the left, 2- charge on the right, so we're balanced. Now we need to make our electrons equal, so that eventually they can cancel out. So we'll multiply this reaction, right? So we're going to end up with 6. So we're going to multiply this by 2 and this by 3 so we can get 6 electrons in each of those reactions. So rewriting them below, that will give us 2Al, gives us 2Al3+ plus 6 electrons. We're going to get 6 electrons plus 3Cl2 gives us 6Cl minus. Okay, so now our electrons will cancel out in the top reaction and the bottom reaction, right? When we add these together, we can add everything else straight down. So 2Al plus 3Cl2 gives us Al3 plus 6Cl minus. And you'll notice, and so we're supposed to balance this now in basic solution. And the way that we balance it in basic solution is that we add hydroxides for every H plus that we have. But in our overall reaction, we don't have any H plus, so we don't have to add any hydroxides. So this is our final answer. So this would be the same whether that's in acidic solution or basic solution. So we're done. Pretty simple. The next one, we've got oxygens and hydrogens now. So like I said before, this one obviously going to be more fun. So we'll write them into two different half reactions. One that deals with the bromine, one that deals with the chromium. So our bromine is Br2 to Br minus. And our chromium, right, we have CrOH3 gives us CrO4 2 minus. All right. So our first step is to always balance any elements other than oxygen or hydrogen. So in the first reaction, we have 2 bromines on the left, only 1 on the right. So we will write a 2 in front of this bromine. In our second reaction, our chromiums are already balanced. We have 1 chromium on each side. So we're done. Our next step is to balance oxygens by adding water. We don't need to do anything for the first reaction because there's no oxygens. For our second reaction, we have 3 oxygens on the left and 4 oxygens on the right, which means that we will add 1 water to the left so that we have 4 oxygens on each side. Our next step will be to add hydrogens, right? To add H plus to balance out the hydrogens on each side. In our first reaction, there's no hydrogens at all. We don't need to do that step. In our second reaction, we have a total of 5 hydrogens on the left, right? 2 plus 3 gives us 5. So we will add 5 hydrogens to the right. So now our chromiums are balanced, oxygens are balanced, hydrogens are balanced. Our next step is to balance the charges using electrons. In the first reaction, we have an overall neutral charge on the left and a 2 minus charge on the right. And we're always going to add electrons to the more positive or less negative side. So we will add 2 electrons here so that both sides have an overall 2 minus charge. In our second reaction, our left-hand side is neutral and our right-hand side has an overall charge of 3 plus, right? We have a 2 minus plus 5 hydrogens, 5 positive. So we have an overall charge of 3 plus on this right side. So we are going to add 3 electrons, right? Because the other side was neutral, so that both sides are now neutral. Now we are going to multiply both reactions so that the electrons are equal, right? 2 electrons and 3 electrons, we need to make them both 6. So we'll multiply this reaction by 3 and this reaction by 2 so that both will end up with 6 electrons. So the top reaction will be 6 electrons plus 3 Br2 gives us 6 Br minus. And our next one, right, we've got waters, and then we've got those guys. All right, so now we've got that where our electrons are equal. So we can go ahead and add these together now. So our 6 electrons cancel our 6 electrons, and everything else we can go ahead and carry down. So we've got 2 waters. We've got lots of stuff. All right, so if we were balancing this in acidic solution, we would stop there. but the problem said to balance it in basic solution. So we need to keep going. So the way that we do this is we add hydroxides for every H plus that we have. So over here on the right, we have 10 H plus. So that means we're going to add 10 OH minus to both sides. So I'll add 10 OH minus over here and 10 OH minus over here, okay, to both sides. When we do that, right, these 10 H plus and 10 OH minus, these make 10 waters, okay? And we have water on the other side, so we need to cancel some of them out. So essentially the way this plays out is that we are going to subtract 2 waters from each side. When we subtract 2 waters from each side, these will be gone, and this will now be 8. So, rewriting this to be neater, we have 10 OH minus plus 3 Br2, and I'm leaving out the phases of matter right now just because I'm going to run out of space if I don't. So there you go. That is the equation when balanced in basic solution. So again, it's the same as balancing it in acidic solution. You just have to do that last step with the hydroxides and the waters at the end. One last type, though, of redox reactions. So we learned how to balance them in acidic reactions and in basic reactions, but there's another type of reaction that's called a disproportionation reaction. And we mentioned this really briefly before in lecture, but I told you we would talk more about it later. And now it's later. So in a disproportionation reaction, a portion of the reactant is oxidized and a portion of that same reactant is reduced. So if you look at this reaction that I've written here, right, we have hydrogen peroxide and it is decomposing. It's producing water and oxygen gas. And so the way that you'll recognize disproportionation reactions is that you typically only have one reactant, right? Normally in the ones we've been doing before, we had 2 reactants, and so we could break it up into these half reactions. But a lot of times in disproportionation reactions, we only have one reactant and then 2 or more, usually it's just 2 though, 2 products. So it's being both oxidized, right? Hydrogen peroxide, part of it's being oxidized, part of it's being reduced. So I'm going to show you how to balance those. So in a disproportionation reaction, we're still going to balance it using the half reaction method. It's just going to be a little bit different. So we're going to write hydrogen peroxide, and we're going to include one of the products, and then write it again and do the other product. So we're still writing the half reaction method. It's just now we're having the same reactant in both of them and treating the 2 products separately. So we would normally go through and balance any elements other than oxygen and hydrogen, which we don't have because we only have oxygen and hydrogen. Then we go through and we balance the oxygens by adding water. So in this first reaction, we would add a water. That would give us water plus water. So I'm just going to put a 2 here. But you could write H2O plus H2O if that makes you feel better. But I'm going to put a 2 right there. And then in the second reaction, again, we're going to balance the oxygens using water, but our oxygens are already balanced. We have 2 oxygens on the left, 2 oxygens on the right, so we don't need to do that step. Now, our next step is to balance our hydrogens using H+. So in the top reaction, we have 2 hydrogens on the left, 4 hydrogens on the right, so we are going to add 2 H+ to the left. In our second reaction, we have 2 hydrogens on the left and none on the right, so we're going to add 2 H+ to the right-hand side. Now we need to go through and add our electrons so that they're balanced. In the first reaction, we have an overall 2+ charge on the left, and we have a neutral charge on the right. So that means we're going to add 2 electrons to this left-hand side. In the second reaction, we have a neutral charge on the left and an overall 2+ charge on the right, which means that we are going to add 2 electrons to the right. And then normally we would go through and multiply both reactions by something so that the electrons would cancel out, right? But the electrons are already balanced, so we don't need to do that. So we can just add them straight down. So our 2 electrons are going to cancel. Those are gone. And if you look at this, actually our hydrogens also cancel. Our 2 H pluses are gone as well. And so now we can just add things straight down. So we have 2 different hydrogen peroxides on the left, so those end up being 2 H2O2, gives us 2 H2O plus O2. So that's how you would balance a disproportionation reaction in acidic solution, and then you could do, you could balance it in basic solution just the same. I will point out that this particular reaction, you could have balanced it just normally because there's no charges. So if you look in this overall reaction up here at the top, there are no charged species in this overall reaction, so we could have balanced it just like any normal reaction. However, I wanted to show you how you would treat this as a disproportionation reaction. So if you have charges, though, you must balance it via the half reaction method because it takes into account those charges with the electrons and all of that stuff. So now that you've watched this lecture, and that's the end of this, you need to go onto Canvas, and under the Chapter 9 module, there is a Balancing Redox Reactions worksheet. This is your lab assignment for this week. So you need to print that out and balance all of those redox reactions. It is a little lengthy. It's 6 pages long, so you will get very, very good at balancing redox reactions very, very soon. Anyway, more next time.